Okay, I think that now everything started. So welcome again. I think today is our ninth meeting here, and last time mm, we start making our solver for our computer-aided analysis package to solve kinematics of multibody systems. Today in practice, I do not have new slides. Yeah, so this is just a refresher from the last meeting, just to kickstart it. Yeah, and so we will go quickly through it to refresh what was told the last time, and we'll get back to coding. Okay, so about practicalities, yeah, we were talking about kinematic analysis of multibody systems. Again, there is some noise here. Okay, perfect. Uh, yeah, so we are talking about kinematic analysis of multibody systems, and we start coding in some kinematic solver implementation in MATLAB. And the work is based on the book as shown here mostly. Yeah, physics hasn't changed for ages, so yeah, this is good. But okay, about some practicalities. So yeah, once again, Cartesian coordinates. So for each body, we put there 3 coordinates, 2 displacements, 1 rotation. Uh, we were discussing this transformation that is shown here, that if we want to get the location of the point that it's located on rigid body, we can use this description, yeah, that uh, if we have this point S, that is and its position is given by a constant point, a constant vector in local coordinate frame, we can transform it in 2 steps. Yeah, firstly by transforming it coordinates from local to global, and this is done by rotational matrix, and then by displacing this vector to the origin of the global reference frame. I hope it's clear. Yeah. Then we are talking how to use those rules to create some joints. Yeah, and for example, here we have a revolute joint. Then we are also talking about translational joint. Slightly different, but the rules are pretty similar. Simple constraints that are just useful, for example, to put the ground on the ground, to make a ground a real ground, not moving object. Uh, Simple expression for those constraints. About the driving bodies, yeah, to keep it as simple as possible. Then, after having a description of the joints, we can go to kinematic analysis on those 3 levels. Yeah. So, and now we are focusing on position level analysis. Yeah. And for this, we need to have the same number of joints as number of coordinates. Here are some expressions for it, and more expressions, yeah, that we will get back here if needed when we will go to next level, yeah, because this is more related to velocity and acceleration level kinematic analysis. Here is our example, and here is our MATLAB code. Are there any questions related to anything in the course, or are you happy, or there is something that makes you unhappy maybe? Okay, there aren't too many complaints, so that's good. uh, so okay, uh, did you get access to the code? Have you found it? Perfect. Okay. So the code is now at GitHub. And by the way, here you can see that after I put it on the GitHub and synchronized with my local machine, here I got this new column in MATLAB, Git column, that states, tells about the state of my repository. Now all those dots are green. It means that the repository is currently synchronized with the online. Yeah, so as not technically, because there can be some changes online. I have to pull them here, but it means that those files are in the state as the files that were registered in the repository. Yeah, so they haven't been any changes. Yeah. Uh, Also, if you go for it, you can notice that there is new menu, source control. I suppose it's not super visible, but you can check it on your as well at your MATLAB if you have a GitHub account, just to manage the, this kind of source code repository. Yeah, we won't go through it. If you're interested, of course, we can go, but in general, you know, if we make changes here from this repository, we can make a commit later. Yeah, it will be somewhere there. View and commit changes. There are no changes, so that's why it's gray out. Then we can push the changes. We can then pull the changes. If there are something else, we can always check it. Yeah, if there is nothing. Yeah, because some issues with configuration, because I use just console to push it, so it works in console, and I suppose that it means that I have to configure some SSH. When you're programming, you always have issues and configurations that you have to tackle, but okay. But now we are here mostly about to create this solver, yeah. And last time we were a little verbose, yeah. So we wanted to make it in good way. We also make some decisions about how the software should work. We also discuss how to store the things in the structure, and we also write some tests and try to modularize things quite finely. Yeah, so this was the last of our state. So we create a function to make an empty system, like make system, yeah, that currently just stores only bodies. In addition, we create a function that adds some bodies, yeah. So here it is. It gets a little longer because we discuss how to store the information into the structure, like a structure that holds the whole our system. And then we are also discussing about how to make things the way that, you know, firstly, you can verify them to some extent, and also that you can provide some default values. Yeah. So it took us a while. Next, to get some indices and also to be used next with get coordinates, we create helper function that tells how many coordinates we have in the system. Pretty simple, but still, yeah. And then we wrote some tests, yeah. So we wrote some tests that check if we add some bodies, that bodies are really there, yeah. We also check that if we add some bodies, the bodies has correct name, yeah. Um, check. We also check some indices, that indices matches. Uh, yeah, we also check if providing some coordinates gives good values, and so and so. And if you have two, if the names matches, and so and so. If the make system works as expected, and finally, if this number of coordinates works as expected. Yeah. Before we'll go to get coordinates, yeah, I was thinking about writing just one more test, because we can still write many others of them, yeah. But at least add one or two tests here that will tell us that the number of coordinates that we are getting from this function after we add some bodies is a correct one. Yeah, because we'll use this function, for example, in this approach to get the vector of coordinates. Yeah. So now we write a test that says does the system with two bodies has how many coordinates? We are expecting to have the system with two bodies. 6 coordinates, yeah? So, so for that, we create a system, of course, yeah? Then we will add two bodies, yeah? So traditionally, the first body, we'll call it typically ground. Then we'll add another body that is link, yeah? Then we'll get the number of coordinates for our system. And then we will check if number of coordinates is if is equal 6. We should correct our message not to be misleading. Okay. And now we will check if this test works fine. We can either run this, and as you can see, after running this, this is not the best approach to run it because it doesn't keep those two parts totally independent, like when you run command run test. But it's first good match that, you know, if it doesn't work, for sure the run test won't work. Yeah, if it works, then we still can check it with run test, but nothing happens, so it's a good indicator because test typically has no output. And after calling run tests, we can see that we have no failed tests. Okay, perfect. Questions? Everything works for you? So now let's back to uh, our main script, and now we'll add some bodies. We already have function to add bodies, but we really haven't created the system properly. Yeah, so now we want to add all those bodies according to the description as shown here. Yeah, so we add just the first body ground, and now we'll add the rest of them. Yeah, so we will do sys and we will follow this approach. Yeah, so here is our coordinate frame 0 0. Yeah, and now we'll add link, so we'll call it link. No, this will be crank. Okay, this is crank. Cheers, God bless you. This is link, and this is slider. Okay, so we'll start with crank, and of course crank doesn't have 0 0 0 coordinates. So what are the coordinates for the crank, more or less? Of course, we can get them exactly, but we don't have to, yeah? What are the good coordinates for the crank? Initial coordinates. Do we have all the data on those plots to get them on this figure? Do you understand what I'm asking about? In practice, here we can see. So here we have global coordinate frame in the last one. Yeah. The global coordinate is aligned with the coordinate frame with the ground. This is typically the case because there is no reason to put ground. Okay, sometimes there is, yeah. But in most cases, you want to keep it at 0 0 0. And here is the coordinate frame for our crank. Yeah, the body number 2. So what are the coordinates of the crank, more or less? in the global coordinate frame. What is the hmm? Yeah, for example, yeah, we can. Yeah, yeah. So do you want to go with millimeters as it's shown here? Because we have to decide on the units as well and be consistent. Okay, so we can put a note here that and what? And radians? Let's go. And so make our system in millimeters in radians. So so what number more or less I should put for x? No, it cannot be. Yeah. You put yeah, of course it's minus, but you put simply far too large value. Okay. Honestly, I don't think that this is crucial, but I'm not sure why you tell about minus 150, yeah, because this distance, what is this distance between the global and local? Yeah, yeah, exactly. So I would put something like minus 100 for x and like 20 for y, for example. It doesn't really matter, the exact values. Yeah, so we can go with those sines, cosines, and get the exact values. Yeah, for 30. Uh, but yeah, but it's not crucial. Yeah. And angle. Angle is very easy. So at least angle we can put here exactly. But what it will be more or less? Yeah, minus 30 degree. Exactly. It must be minus. Yeah. Or because you always calculate, at least we agreed that we'll calculate in one hand side direction starting from the global x or the axis that is parallel to global x. Yeah. So here we have x, and because the angle we can measure it, for example, in this direction, then it will be negative 30. Yeah. Is it clear? So we can put minus dec to rad 30. Okay, and we add crank, yeah, and with the same way we'll add the rest of the bodies, yeah. So the next body to add is add and for link it will be it's 300 plus 200 minus something, so let's say that it's minus 400 for x, yeah. For y it is also something like 20. It doesn't, I think it's more, but especially in the first one, but yeah. And the angle, what is angle here? It's also not very crucial. Yeah, we can see just that the angle is most likely smaller than this 30 degrees, is positive, because if we go from global x, it's clearly rotated slightly right. Yeah, so it's some small positive value in degrees. So dec to rad, for example, 10 degrees. Good enough. Okay. Uh, Joints? Yeah, they are. Yeah, of course, this is the case. Yeah. Um, we have to be aware of it. So, of course, so it depends. Uh, we don't bother here with it because we will solve the problem on kinematic level. Yeah. So we'll fully define the system. Yeah. So for us, this task will be pretty easy because we know, because as I understand, you are worried, you are concerned that if we put those coordinates, yeah, then those joints won't be in the proper places, and they won't be. Yeah, uh, we want to get it close. Yeah, but then we'll solve this system on the position level using some of those methods for solving nonlinear systems. Yeah, because we have this equation c equal to 0. Yeah, so by using this kind of not exact values for coordinates, we'll have c not equal to 0, but we know how to solve for c equal to 0. Yeah, so knowing this, we can use those values that are more or less correct. Yeah, and then leave it for solver. Of course, putting the exact values would have this advantage that then we can verify that C should be 0, and if it's not, it means that we make some error with modeling. Yeah, but we'll have test for it. And then we have the last body. That is slider. And slider is located, it's fourth body, it's located here, so it has some large negative value, like minus 500, for example. It has clearly 0 at y and 0 for the angle. Okay, and this is our system. Yeah, four bodies. Four bodies are defined. And I hope that now you can see what is about this general solver, yeah? That instead of, solving something specific, yeah, we are making this by declaration, yeah? So we are creating the system that we are adding the bodies. And simply, if you add more bodies and more joints or less bodies, less joints, you can, with different coordinates, you can, by declaration, like here, define another system. Yeah, and the procedures are the same. Yeah, so we will here use this software to solve this system slider crank that we just defined now on kinematic level, yeah, on position level like today, and hopefully also for velocity, but simply by uh, just rearranging those comments, but by providing different bodies in different locations, we can define different system and solve it using the same methods. So this is the reason about claiming that this kind of the software and solver is general. Okay. So now we can display that. Yeah, this is always. So let's create one simple function. Number of bodies. to use it there. And we won't get to any larger extent. Just write it as simple as possible. Of course, currently its implementation is really simplistic because n is simply length of cis bodies, but because of many reasons, it can be more complicated. Okay. And here we can use those it's always good to check because we can simply, because our interface, for example, also has some requirements that we have cis on both sides and others. Yeah, so if we missed cis somewhere here on this side, nothing will happen, no error will appear, but still our system can be incorrect. Yeah, because we didn't retrieve it back to our way. So it's always a good idea to check if we get what we are expecting. So we are, of course, expecting to get system of 4 bodies with how many coordinates? Of course, 12 coordinates. Yeah. So let's just make it run. And yeah. Not too many surprises, which is good. Yeah. We don't want to write our program to make too much surprises. We have another means for that. Okay. Can we proceed? Okay. Uh, so now next step is to get coordinates. Yeah. So now I will make it a cell so that we don't have to call everything. Yeah. Again and clear the system. So to get coordinates, we simply want to have something like Q, because Q is, in practice, it will be Q0, because it will be just initial coordinates. Uh, how to call this function? Hmm. Any ideas? Wait. On the system level, yeah, we have this kind of representation, yeah. So C and CD from Q equal to 0, yeah. And for example, for our Newton-Raphson method, if you maybe recall, maybe I can just open it here. I can already copy it here. Yeah, so was it here? Okay, here I also have it. So why not? So I will put it, our Newton-Raphson method here, yeah, because we will use it later on. So for example, for Newton-Raphson method, you need a function. It will be our C. We need a Jacobian. It will be our CQ. Yeah, and we need X. which is vector of the parameters that we want to get. So for our system, this is the vector of coordinates. Yeah. So in general, so to make all this work, yeah, we are having those bodies, and then we have to assembly within the formulation using Cartesian coordinates all the entries for the whole system, yeah, to make it work. We are not working body to body or joint to joint. We are working on those entities globally, yeah. So to solve this, we will have a functions that create a vector of all joints, constraints in practice, yeah. Then we'll have a function that create a matrix of all the matrix of the Jacobian for the whole system. And also we need a vector for coordinates for the whole system. Yeah. So now we have those coordinates attached to each single body. But to work on the system level, we just have to organize them and group them as a one vector. Yeah, it can be. So do you want to call it assemble coordinates? Okay. Because we are, okay. We know that we are assembling the system, yeah, so assemble coordinates and assemble the coordinates from the system, yeah, so this is the function. Uh, and oh, so I will close that one, put here some new lines. Uh, okay, so I just put here the note that the vector will store coordinates for each body in order, yeah. So the Q will be, looks like x1, y1, phi1, yeah, x2, y2, phi2, and so on and so on, yeah. Up to xn, yn, phi n, where n is the number of bodies. Okay, clear? Uh, so first here, let's create, okay, can I, okay, convert to function, nice. Okay, I don't know if this will work. No, it's not working because it won't refactor it. I just create a new function. So, okay, let's fix the name. Oh, they have. I don't know. Okay, I don't want to fight with it. Assemble coordinates. Okay. And here we have some already description. and we know that our output is Q because we already defined it in our main script, and we know that our input is simply sys because sys holds the bodies, and based on the bodies we can get all those coordinates. Uh, Also, we are not returning sys because we will not make changes to our sys because the coordinates were assigned where the bodies were added. Yeah, so we are not, we are just reading those information. Yeah. Okay. Ideas how we should proceed. Of course, we can make it in many different ways. Yeah. So because we want to create a vector for the system. Yeah. Mm, I always do like that, that I will allocate the memory for it. Yeah. So I will just write that Q is equal to zeros. What is the size of the zeros? How many? Yeah, of course. So we have already this function number of coordinates sys and 1. Yeah. And then we have to, put here in this vector the bodies, the coordinates for each body. So we have to write a loop. So for loop, for what? B equal to sys bodies. So we will loop through whole bodies. Okay? Make sense? Were you expecting this? Okay, good. And now, is here anyone brave who know how to write this one single line of code? Because we just need here one line. Yeah. But where we how to get it? Because okay, here you can see that I already make assumptions that all the we need is in body. Yeah, because I do not have here even index, number index, so we cannot, number the stuff. Yeah. So the reason for this is we can go to add body. Is that we put in body name. Yeah, we don't need name for coordinates. Yeah, but we have initial coordinates. So this is where the values are stored. Yeah, so we will put them on right hand side because we will want to get those values copied to Q. Yeah, but we also have this coordinate indices. Yeah, so this is the location, and those are the indices that help us assembly all the matrix that we will assembly them with respect to bodies. Because here we will assembly the bodies in two ways. Yeah, one it will be with respect to bodies, and another will be with respect to joints. Yeah. So to have it with respect to bodies, uh, we have this coordinate indices. So Q of B coordinate indices is equal to B okay, none of those shortcuts works, so I'll just copy it. I just change the name to Q0. because it in practice it better serves the purpose. Okay, and we are able to write it in that way simply because of those design choices that we have made. Because we could of course make different design choices. Yeah, this is just one of those. Yeah, so we decided that uh, well, by oversee that we will assemble it. Yeah, so we put here indices and values are just values. Yeah, make it sense? Does it look like it should work? How can we check if it works? Yeah, of course, make it some tests. So at least write some simple tests. Yeah, new script, test assemble coordinates, and we'll just write. Let's just write one test. Yeah, so okay, so add to bodies and check the vector of initial coordinates. Yeah. So of course we have to create a system. Then we have to add to the system two bodies. Let's call it ground. And let's put it at location 1, 2, 3.5, because why not? Two bodies, so let's say it's pendulum. We know that it doesn't really matter, but 0, -7, 12, and 14. To write the test, we have to define what we are expecting to get. So what we are expecting to get. Yeah, based on those values, yeah. So we are expecting to get firstly those values, and then those values. So now we just call the function and now right, first assert. I will simply check that if length of Q0 is equal to 6, because we're expecting this to have it length of 6, yeah. And then now how to check if the values in those vectors matches. Do you remember? How to check if those vectors, two vectors, are very close to each other? No, not integers, there are doubles. Like here you can see. Yeah, when you have integers, that's true that you can just compare them easily. Okay, they should be the same because it's copy-paste, we know this. But yeah, let's not be too keen to assume it. Yeah, we want to check that, do you remember what we are discussing? That we want to get those values very close to each other, yeah? Yeah, exactly. So how to get this, but how to get the notion of the closeness of those two coordinates? Because now we have two vectors, 6 by 1, yeah? So how to get the information if those vectors are close to each other? And it must be expressed by one number. how it's called, something like that. No, EPS function can help us to get tolerance. It's called the norm of the vector. Absolute value from difference is one of the norms. That's true. But in general, this term from F is norm of the vector. Norm will give you some notion of closeness. There are different norms. We are not, here concerned too much about which norm we are using. Yeah. So we'll just use default norm. And the norm is for Q expected minus Q0. Yeah. So we want this norm to be close to 0. Yeah. Norm is always positive number. Yeah. If the vector is 0 vector, norm must be 0. If it's positive, it should be small value. Yeah. Here, most likely it will be 0, but do not rely on it. We will check that the norm is smaller than, for example, 10 times APS of 10. Okay, and now hopefully it works. Yeah, it works. Is it clear, all that stuff, why it is what it is here? Okay, good. So now we should be able to run this cell. I have to once again check what is the shortcut to... Okay, shortcut is pretty. Yeah. And we got the number of the vector of coordinates as expected. We can check it here, that first three are 0 as for the ground. Next three are like here. Next three are like here. And the last three are like here. Everything seems to match. Good. So we have this, this part is done. Now we need simple constraints to make it work, revolute constraints and driving constraints. Okay, so we have to add simple constraints. So we are adding bodies. Now we'll be adding constraints. Okay, we'll be adding simple constraints. So we know that constraint is characteristic of the system. So we'll add those constraints to the system. Yeah. So we'll have sys is equal to add what? Add simple constraint or add constraint simple. And we know that the first uh, the first parameters must be system. Yeah. Uh, what should be the next parameter? No, we have here type of the constraint, simple constraint. So we know what is the type. The next one, yeah, which body? How because we are like here, yeah. We have here simple constraint, so we have here this index I. That it's index I that says what is the button ID, yeah. So we have to somehow denote here a body. So how to denote here a body? Because we can also do this in multiple ways. What is a nice way? You think it's nice way? Yeah, because yeah, we are not using them here, so you don't know how the bodies are stored. Yeah, the name of the body can be solution. So can we use the name of the body? So ground, for example. And now we need one more. Yeah, we need one more because we have three types of simple constraints. Yeah. So we have the constraint for x, for y, and for phi. Yeah. So now we have to somehow denote the type of our constraint. If it restricts the motion in x-axis, y-axis, or if it restricts the motion of the angle. So we are expecting here to get the third parameter and how to define it. What would be the way that you like? Yeah, we can do this. So we mean to put it like that, yeah? So we are constraining x coordinates for the ground. Yeah? Is it okay? We can use 1, 2, 3, we can use -1, 0, 1, we can use longer names, shorter names, we can, but yeah, we can as well use this one. And we have to decide somehow on what we are going to use. So let's go with this approach. So let's keep things simple, yeah? And so for the ground, we need three simple constraints. On x, y, and let's say phi. Is it okay? And of course, we have to implement this. And to implement this, okay, let's go step by step. So first, let's create a function for it. By the way, if you can see now, those indicators for Git has changed. Yeah, that because we add somebody, so they are just empty circles. and we have modified some bodies. So they created some rectangles here, yeah, squares. And by the way, like this we have modified like this, yeah, this file. Then we should be able to go to source control. We can of course commit it, but we can compare it to, I think, ancestor. So for example, you can see what changes in this file we have made since the last commit. Yeah, so for example, we put X here, we change those to cells, remove that part. Oh no, add here some comment and add all those parts. And we can do this for all other stuff. Then to make it work, we should add it to Git. Together with this test. And of course our file. Okay, so it's not working that way. I rarely use it, so. And then we can view and commit the changes. So we can select the files that we want to include in our commit, yeah, and then write a message that you cannot, I suppose, see because, you know, again, this font is not very consistent. Write functions to get system coordinates. Yeah, because we have done it, yeah, in practice to add system coordinates. Then we can commit it. Because connection is not really working, I can go to terminal. Go there. Yeah. Go there to our system, MATLAB code, software, and so it's pretty long. Yeah. So I check the status that can I increase this font? Well, maybe I can, but it's not the most important. So I add those files, commit those files with the message that we add coordinates. I push those files to Git. So now if you go online, you can download the current version. Without any method because I haven't added because we haven't used it yet. I would add it later. I haven't added here because it's just a temporary file, but all the rest is already available for download, an updated version. But okay, uh, so this is the way this version control works, but let's get now to adding simple constraints. And we already put a header, so we have system as the input. System, body name. And what is the last? It's constraint coordinate. Okay, a definition of the simple constraint to the system. Okay. And now what we have to put here? We have to put here some kind of structure that will hold the information that will allow us to create what? To write this kind of constraint for the system. Yeah? Make sense? So we have to write that our constraint, for example, is a struct. Okay, we can just use simple approach and just use dot notation, yeah? So what fields are needed to write constraint equation for simple constraint? Equation is here. So what do we need to write this equation? By our program. Uh, you, Now you are talking not quite silently, so I haven't heard. No. No, it's not the purpose for this function, yeah? Add the definition of the simple constraint to the system. Now we are gathering all the information because there is no really use for it, yeah? Of course, we have enough information to write those constraints, yeah? But now we are defining the system, yeah? So we are defining the system. So we are putting all the parts together, like we put all the bodies there. Now we'll add to the system all the joints, and then we'll use the information about what are the joints to solve our system. Yeah, because now if we solve it, it's not very useful. Because what then we will do if we would solve it? Yeah, we are not in the place like here. Let's close all that uh, to solve it. Yeah. Okay, makes sense. So we want to store all this information and then use it in different contexts. Yeah. So now we want to create a structure that will allow us to write those equations. So the question is, what do we need to write those equations? Here's equation, yeah? So what do we need here? Yeah, kind of, yeah. So here you can see that here is some coordinate, yeah? In all those, here is some coordinate minus some constant value, yeah? So we need firstly coordinate ID. And then we need coordinate value. For example, yeah, is it enough to write this kind of equation? Can you see that this is enough? This is enough because we already have vector of coordinates q0, yeah? So we'll operate a vector of coordinates. So we want to write this as equation based on the vector of coordinates. So we have to know where this coordinates is located. It doesn't really matter even for this kind of constraint for each body, which body it is, yeah? Because it will be always in the same place. So we just need exact place, yeah? This coordinate is connected to somebody, but you know, it's not the information that is interested here. What is interesting here that we just have some coordinate. And we have to keep this coordinate to have constant value. Yeah. So how to get this information? Yeah. How to get from those inputs what is coordinate index? Yeah. For the body name and what we are constraining. Yeah. So firstly, from the body name, we have to get a body, to get indices of this body, to know what are the coordinate indices. Yeah. So first step is to write a function that will get our body based on the system and body name. So this will be the first step. So it returns body based on the system and name, or body name, to be more precise. And it is very simple function that just loops for each body for be in cis bodies. Simply if it checks if we just call it name, great. If b name is equal to body name, it's enough to writing something like that. So we loop through all the bodies. If we find the body based on body name, we just return the body. And break the loop because uh, it's not perfect. Because if we get here, it means that there are no bodies. Yeah. Should we handle this case that there are no bodies? We should somehow. Simply because, we will get some strange errors. And it's super easy to make just error in the name or something like that. Yeah. So how to handle this? We can just write an error. Okay. We should write a test for it, but writing test takes us a little too much time. And if you want to finalize this, we have just 1 hour. I think that we should skip the test at least for now. Yeah. So it's very good practice, and it for sure it's profitable for all that stuff. But simply due to limitation of the course and time constraints, we have to skip it. So we will just check if it works simply based on our system. So something is clearly incorrect. What? And is missing? For what? No, it doesn't matter. Oh yeah, of course. Yeah, you're right. So I put here this break, but that's true. Yeah, so you're right. So simply uh, we can put here something like that. That put if is empty body, then we are putting this error. And here about your comment, simply if you have just one function in the file, we can just skip the last end for the function. So it's optional. If we want to put here multiple functions, that we either have to skip end for all functions or put end for all of them, yeah. So it's typically better to put all of them, but if there's just one function in the file, the last end can be skipped because it's just the end of the file. So yeah, you are right. Yeah, good. So now when we ask about the function with the name ground, it just returns our fill returns as it this for us. And if we make a typo here, it returns the error. Good. Great. Questions? By the way, there is one issue here. I don't know if you can spot it. That we can add the bodies with the same name and nothing will happen. Yeah. And this is not very nice, but we'll just skip it. Because then we have to put, of course, we could solve it. For example, by checking here if the name is unique, if it's not in the system, and then put some error, yeah, and so and so. But uh, don't get things too complicated. Uh, so okay, so this part should already work. Yeah, so we are able to get our body, yeah, from our system, and now we have to get coordinate index for it. So simply we'll use the here switch. Does anybody remembers how switch works or knows? Or maybe we'll use if. Okay. Do you prefer if or can we use switch? Yeah, so let's check it because I'm using it pretty rarely. So switch case otherwise, exactly. Yeah. So switch expression cases and then otherwise. Yeah. So it should looks like it's like multiple if. So here we have expression to which we will compare. the cases. Yeah, so we compare it to a constraint coordinate. Yeah, and we define that fair case will be x. Yeah, next case will be y. Final case will be phi, and there is also otherwise. As you can guess, otherwise is executed when none of the cases is met. Yeah. So I will create here local coordinate simply to indicate the body coordinate index. So coordinate index of the body with respect to the body. Yeah. So of course x is first coordinate, y is second coordinate, and phi is third coordinate. Otherwise, we should put error because we don't know what to do if we have coordinate that we cannot recognize. Okay. And now we can write that coordinate index is b. It's simply like that. Okay. So here we will get indices for the body. And then within these indices, we will check which one is it exactly to get this one number. Because we put them at x, y, z, x, y, phi, yeah? So that's why it worked that way. Make sense? So now the question is how to get coordinate value. We have two options. Either we declare it, so we put it while we create a constraint. So possibly here we have to add third value that tells what is should be the value of this coordinate. Or we can assume that the initial value of the coordinate is correct. Which sounds better? I think that, okay, I would assume that it's better to put it here. So for here, it would be 0, 0, and 0. Yeah. And simply add simple coordinate, we'll have uh, coordinate value. And that's all. Okay, does all this make sense? We'll just make one shift. We'll put this as a function because it's too long to keep it here. So here we can use convert to function, and we will use function get local coordinate ID. because it gets a coordinate ID, but with respect to local frame. Yeah, that's why it returns just 1, 2, 3. Yeah, based on the name, it returns this coordinate. Okay. Have you have you seen what I have done? It's called code refactor. Yeah. So I just select this function like that part, and then you can select convert to function. Then it just asks you about the name and try to recognize what are inputs and outputs. Yeah. And then we can use it in different functions if we need it. Yeah. Most likely it will be needed like in the driving constraints because it has very similar, works in the very similar way. But okay, uh, is it completed, this function? No, it's missing two small components. The small components came somehow from here, that it would be nice possibly to have indices for our constraint as well, because simply as we discussed here, we'll assemble some system matrices with respect to bodies to have coordinates, yeah. But we also assemble our system with respect to constraint. Like for example, we assemble C vector, yeah. We have to, we have just a vector that has number of entries is equal to our number of coordinates. But of course, we have to put all our constraints in specific order, yeah. So we have to keep it somewhere. We can keep it here, yeah. So we can have here constraint indices, yeah. And of course, it's not equal to 1. Then, as you can see, there is a lot of coding everywhere, yeah. So because it must be equal to the actual number, yeah, when we add those constraints. And how we solve it for body, we get the number of coordinates plus something. So now we'll also use the same approach, but we'll have just the number of constraints plus something. Number of plus 1. Okay, good. We don't have this function, but we'll write it soon. And now after we create the structure C, the last step will be also the same step like in the body. We have to add those constraints to the system. Yeah. So system, for example, something like that. And something like that. Does this all make sense to you? There are two issues here in this code, that this code won't run because we don't have this function and we don't have those structures. Okay, so first we have to get back to make system and put here. So in the system we put structure bodies, yeah, but we should also put this new structure that we are requiring here. So in the make system we have to have constraints. simple equal to empty to be able to edit. Make sense? Yeah. And now we also need function number of constraints. Uh, and this function returns n from the system. Firstly, n is equal to 0. Yeah. And this function must, how we solve it in bodies? Number of bodies was quite simple because it was length of cis bodies times, okay, so it was number of bodies, but rather number of coordinates. So it was 3 times length of cis bodies. Yeah. So here for number of constraints, now we can put, because we have just one type of constraints, we can just put length of cis. Let's create a new system. Cis constraint simple. As we have just one type of constraints, and those are just simple constraints, and each simple constraint has just gives is just one equation. So one simple constraints relate to one number of just constraint, yeah. Because with revolute joint, for example, it's complicated. It has 2 constraints. Simple constraint is simple, so it has just one constraint, yeah. Okay, and this should work for us now, yeah. So just n number of constraints will be equal to length of simple constraints. And now this function should work. Okay. So let's get back here, run it from the scratch. And let's see, now we have constraint as well. We have 3 simple constraints as we have added them. And they are for coordinates 1 to 3 because we constrain the ground. X, Y, and phi in the ground relates to 1, 2, and 3 also in global coordinate frame. And we assume that all they will have values 0, 0, 0. And because those are 3 first coordinates, their indices are also 1, 2, and 3. Does all this make sense to you? Perfect. Any questions? Did I get you lost? For sure I did. Okay, not sure, but it's likely that I get you lost, yeah? Do you have any questions to any parts of it? So let's close it. Add all this to Git. Okay, okay, this is the last one, so it's not. Now we can view and commit changes. So we'll add all those bodies, yeah, and all those changes were just to functionality to add simple constraints. Okay, so once again, yeah, if you get lost, you can download it from Git. Slender calc, yeah. So we add those simple constraints. So now is another question. Because here we have our example. So have we defined all the simple constraints that are existing in our system? No. How many of them we are still missing? Or which one? Just which one? What we are missing? Hmm? Yeah, for the slider. Yeah, of course. Because we can put it as transactional joint or not. Yeah, here we will use it for put it as simple constraint. Yeah. So those three are just to put ground immovable. Yeah, fixed. So now we can add slider. And what coordinates of slider we want to get fixed? Y and phi, because it's moving in x direction. So x must be free, so we cannot fix it. Yeah. So we are going to fix y and phi. Y and y will have value 0. And we will do for slider the same from the phi and also 0. And if we run it, we can get it from here, put it here, system with bodies, coordinates, and here we can put number of and run it again. We have a system with 4 bodies, 12 coordinates, and 5 constraints. Yeah. So we are expecting to have this kind of the system. Of course, to solve it for kinematics, we want to have system with 12 coordinates and 12 constraints. We are working on it. And we have 5 simple constraints, 1, 2, 3, and 11, 12. As expected, because slider is the last one, so we are also constraining y and phi of the last one. Yeah. And those are in order, 1 to 5. Questions? Okay, now we can find it on the internet after I push our Git changes. Okay. So now revolve joins. Yeah. So now we want to add and let's start with the header. Yeah. So add revolve joint to the system. Revolve joint must be added between two bodies. Yeah. So ground and What is the first body? Crank. And now, what is needed for revolute joint? Do you remember? Because of course we have to know which bodies we are connecting. This is clear, yeah? Like here, yeah? We are connecting first body with second body, so ground with the crank, yeah? What else do we need to know to define a joint? Yeah, location of the joint. Again, we can provide this information in many ways, yeah? The direct way is just to provide coordinates of the joint point, joint location in local coordinate frames, okay? So we can do this by providing here location at ground, 0, 0, because this joint is located at 0, 0 for the ground, yeah? And what is location for the crank? Exactly, 100 and 0. Okay, and now new function add revolute joint. And we know that it returns sys. It accepts sys. Body 1 name. Body 2 name. S1 local. Okay, is it clear? So of course we need the bodies, we provide the names for it, and the local coordinates of the joint. Let's call it S, like it was, I think, on the slides. Yeah. We can call it, do you want to call it 1, 2, or IJ, like it was on the slides? Okay. Body I name, body J name, SI, and SJ. Okay, so we are adding definition of the revolute joint to the system. Again, we can just start with defining structure day, and we have to define it in the way that we can write this equation. Yeah. Again, we can define this in really many ways. Yeah. But if you want to be consistent somehow, for example, with the simple constraint, it's enough to know the coordinates for part A and vector, and as well coordinates for part J and a vector. Okay. Now I'm thinking if we shouldn't try to write constraint vector for simple constraints to make it clear why we have chosen. But okay. Let's do this and then we will write constraint equations, okay? So for simple constraint, we get just coordinate indices and values and constraint indices. Yeah. So for sure we will have constraint indices because we just need them. So this is just general property of the constraints. And it will be equal to number of constraints in the system. Just the difference will be that it will be plus 1, 2. Because each revolved joint has two equations. Yeah, so we need a spot for two constraints for each revolved joint. Yeah. Here we have also those coordinate indices. But here we can just put body I indices. Yeah. And what we else need? We just need those points. Okay. SI local, SJ local, and body indices. How to get body indices? Do you remember? Yeah. We get the body and then get body indices. Yeah. So we can here get BI is get body system body I name. Yeah. And then we can get this body coordinates. And we can then do exactly the same for body J. So body J is body, we will get body based on body J name. And then we can write the indices of body J or get just from body J. And this should be all. Yeah. Now we of course have to repeat this step. We want to add revolved joint to our system. Yeah. We know that we don't have revolved joints in our system defined yet. So we have to open again make system and add here empty revolved joints. Yeah. The next thing that we have to go to number of constraints and add here 2 times length of sys constraint revolute. And now everything should work. Questions? Can we go and test and see what we have stored and if it makes sense? So okay, now we have added just one revolve joint, but before we'll go with others, let's run it from the start. Yeah, so we have 12 coordinates and 7 constraints. We got because to the 5 that we have previously, we have added one revolute joint, so extra 2 coordinates. So now our system has 2 fields for the constraint, so 5 simple like it was, and just one revolute. Revolute is the new one. And for the revolute, you can see that we have indices 6, 7, because we have 1 to 5 for simple. Now we have 6, 7. 1, 2, 3 is simply the indices of the ground, the first body, body I. 4, 5, 6, second body, because crank is second body. SI local 0, 0, as we defined. SJ local 100, 0, as we defined. Make sense? And now we can add the remaining revolute joints. So we can go to our example that it's here, and we are still missing 1, 2 revolute joints. Yeah. So the second revolute joint is between crank and link, and location at crank is minus 100, 0. Yeah. So it's here minus 100, 0. And for the link, location of this joint is 300, 0. Yeah. So it's 300, 0. It works. 9 constraints. And for the last, we want to connect link with the slider. And for the link, I think it's minus 200, 0. And for ground, for slider is 0, 0. Yeah. So for the link is minus 200 because it's this point minus 200, 0. And for slider, it's located at the position of at the revolute joint, so it's 0, 0. Yeah. So now if we run everything, we have 12 coordinates and 11 constraints. To solve our system, we need one constraint, yeah, more, to have full rank system. So now, how to do this? How to get it? Of course, it's written here as well. We need driving constraints. First, let's add all this to GitHub. Let's, okay, no, I don't want to edit this to GitHub, but okay, I already added, so I will just skip it here. I will add everything except this, Functionality to define revolute joints, commit. And let's push the changes so we can get the code already. Driving constraints. We need one driving constraint that will tell us that this crank is rotating with the specific velocity. Yeah. So let's add driving constraint. Yeah. And it will be very similar to the simple constraint. Okay. It will be very similar to the simple constraint. Because it has very similar structure. Yeah, just instead of having some constant value, we need a function of time. Yeah, so we'll add driving constraint to the system. We need to add it to crank. We want to, of course, enforce the motion for our phi. We could also add it to, for example, slider. But yeah, but it is defined how it is defined, yeah. Or to also we could also add it to the link, yeah, because we can add it almost everywhere, yeah. But okay. And here we need to provide function of time. Simply. Yeah. So we provide function of time that is equal. We know that at start this angle is minus 30. Yeah. So the constant value is minus plus omega, and omega is 1.2 radians per second at 1.2 times t. So this is our driving constraint. Make sense? That we apply it to specific body and specific coordinate and provide it with the function. Do you want to see the slide with driving constraints? Okay, so just to have reference here, where it was. Oh, it was here. Yeah. So for simple constraints that we have already implemented, we have the constraint in the phase that specific coordinate is equal to constant value. Yeah, so we fixed something. And here the difference is that we claim that specific constraint is simply equal to some function of time. So it will follow some function of time. Almost the same, but like that. And we just use exactly this expression. Yeah. So that like here, this is driving link. In our case, it's called crank. We have initial value of the angle plus omega t. Yeah. We can even make it even more obvious by writing that phi crank 0 is equal to that number and put it here. And our yeah. It's a good point if it's negative or positive. Yeah, I don't remember. So let's go back here. Yeah, it's negative, of course. Yeah, you're right. Yeah. So it's minus. Yeah. Yeah. So this makes it even easier. Yeah. So it's minus 1.2. Of course, we need function for it to make it, but because this is very similar to simple constraint, I will just copy simple constraint. But of course, when you copy something, you have to be very careful. Yeah. If I understand correctly, okay, so first of all, we derive the simple constraint as we will tell what is the location of the local coordinate frame of the crank. Yeah. So this phi 0 tells, where the local coordinate frame of the crank is located at time 0, how it's oriented. Make sense? Okay. So we copy it here. We have to change this name, add here, and just go. So we tell that we added to the system, but the name constraint coordinate is the same, and here is not constraint value, but constraint coordinate value, but coordinate function of time. Yeah, so this is coordinate function. So we change this name, so we can already change it as well here. Add driving constraint, add definition of the driving constraint to the system. Okay, get body name because we need the body here for indices, and get C index of the crane. So this is the same because coordinate index is defined in the exactly the same way. Then we have coordinate function because we need to write our equations of constraint equations. Constraint indices is the same because it's one number of constraint to sys, and then we are adding sys constraints driving to our system. Yeah, so we have to do the same as previous, that we have to modify make system to add new structure for driving constraints. And for the number of constraints, we have to also account for our new type of coordinate constraints. So for driving constraints as well. Yeah? So here plus length of system constraint driving. Okay. And now if we run it, we should firstly hopefully it work. Yeah? And then we should get a message that we get a system with 4 bodies, 12 coordinates, and 12 constraints. Let's see. Yeah. So our system is fully defined on kinematic level, and now we can solve it. We can put check here that we have driving constraints. One point is missing. That we need still constraint equations. But okay. But we are still one step further. So we have defined our system, at least on this level, that we define all the bodies, all the joints. And now we start thinking about how to solve it. So to solve it, of course, we want to solve C of Qt equal to 0. Yeah. Uh, yeah. So we need C. Yeah. So what next part? What do we need is our constraint equations. And simply, we would like to write that C is equal to, for example, what? Just constraint. We would like to write it in this way. That is just equal to constraints, Q0, and 0 as a time, for time 0, because it depends on time. Yeah. Make sense? So we need this function. And here we have C, so constraints based on Q and E. This function return the vector of constraint equations. Okay. we can initialize it. Of course, okay, one thing is missing here. Of course, we need to provide a system for it as well, right? Because without the system definition in the system, we have information where constraint, what are the constraints, yeah? So here we have to provide the system as well. Now we can write that C is equal to zeros by default. Number of constraints for the system, 1. And now we can write that for S equal to and put things here. Let's put things just here, yeah, in this function for simplicity, yeah. Because after all this definition, so same for constraints, we have to know where to put this equation. And this equation, we can check again at simple constraint, how we call it. We call it coordinate indices, yeah, coordinate index, yeah. So this is the place where we should put our constraint, yeah. Constraint equation is on the slides, so let's get back there again, yeah. So it's like that. So it's simply to get coordinate. Coordinate is located at vector q, because this is vector of coordinates. We of course have to get just specific coordinate, and we already thought about this. Let's close most others, and we just put the ID of this no, okay, so sorry, constraint indices. So here it goes constraint indices because C is constraint of constraint indices. And now we are talking about coordinate. So we have coordinate index, one index for the coordinate. So coordinate minus constant value, yeah. So minus and so of course it is located in structure S, and this constant value is S coordinate value. And that's all. Does it work for you? We can already test call it, yeah. Okay, this is that doesn't belong here, it belongs here because it belongs to the definition, yeah. So here we can call it. It's still not completed because we didn't put there, for example, revolved joints, because we are not expecting it to be 0. But for the simple constraints that we implemented, we consider it to be 0 because we put those values exactly, yeah. However, if you were, for example, to put here that for slider, it's, for example, 0.1, 0.1, because, for example, the figure is not perfect, yeah, then we should get some values in the constraint vector, because the constraints, simple constraints for the slider are not met, yeah. So let's check it. And as you can see here, the constraints here, 1, 2, 3, 4, and 5, has those values, yeah. Because we added firstly 3 constraints for the ground, and they are met. Then we have those 2 for a slider that are not met, and it works, right? It's shown here. So let's continue. And Just proceed in the same order. We start with a simple constraint. Next, we have revolve constraint. Yeah, so for R equal to sys constraint revolve. The start is the same. Of constraint indices. And here is equation that we want to write. Yeah. So first we need Ri. Ri is located in Q. And in revolved join, we have body I. Maybe it should be indices, but let's leave it as it is. Yeah. So body I index. So it is R body I index 1, 2. Okay. Plus. And then we have A and SI. A is just rotational matrix, so let's call it rot. And rotational matrix depends on body coordinate 3. Yeah. Times R SE local. Yeah. And the next we have minus, similar but for the J. Yeah. So it's minus that part for body J. So coordinate of body index 1, 2 goes to position. And minus similar thing Q R body J, so rotation of body J, and SJ local. Does it make sense? The only issue is that we don't have a rot function, but let's just fix it with adding function rot. Function rot is of course rotational matrix. So we call it A, and it's based on the phi. Yeah. And there was simple equation for A, like and we have it here, like cosine minus sine, sine, cosine. Yeah. Cosine phi minus sine phi, and then it's just sine phi, sine, cosine. So this is just our rotational matrix. Yeah. And this is our equation. Yeah. So this is in practice, we can write it in more readable way by writing that Ri is that part. Yeah. Phi I is that part but 3. Rj is that part but for body J from the indices. Yeah. Phi j is this one just with index 3. Yeah. And then we just have here R I, rotational matrix of phi I plus r si local, yeah, and here we have minus rj minus rotation of fij plus rs local. Okay, and now when we run this, hopefully it run without the errors, then we have a bunch of new numbers. Yeah, so we're not so close, but good enough. Yeah. It won't be good enough to make the abolition of this, yeah. And now we are left with the only with the very last constraint. Yeah. So we just need the constraints as well for driving joints. So let's call it D. For D equal to sys constraint driving, we will copy this as it is very similar to it. So of course we have here D. I will close it. Constraint indices. Of course we have the same coordinate, but here, if we get to our slides, the difference is that we have here this value for driving body, yeah. So this is dv, let's call it. Now let's open our driving constraint to see how we call it. So we call it coordinate function, yeah. So maybe it should be rather CF coordinate function. It's super local, that's why I use this short name. And we know that it requires time, yeah, because we put it as a function of time. So this is the place we use phi, and simply put it here, put the here because this is in this field, yeah. So simple, the very last constraint that it's a driving constraint, it is in this indices, but we use it consistently, so it's nice. And it says that the coordinate that is defined is just equal to this function of time, like that, yeah. Make sense? And now if we run it again, of course we see no change because this is 0, but to see that it works, we know that we defined that crank. So let's put here 31 degrees, yeah, just to see some difference. Okay, now I have to, okay, now we can see this 1 degree difference at the very end, because it was 0 and now it has some non-zero value. Make sense? Can I just spend with you the last 5 minutes to make something useful for it? So now we have that part, and now test call to fsolve, yeah. So let's add all this stuff to Git. It's not so easy. So to have the checkpoint, let's add everything except again this Newton-Raphson method. So so now we computed constraint equations and push the changes. Good. And now we want to get constraints equal to 0. It can be done in many ways. We'll use Newton-Raphson, but to use Newton-Raphson, we need Jacobian. And of course, we don't have time to compute Jacobian now, but we can just use fsolve, as is written mm, here. Fsolve, yeah. Solve system of nonlinear equations. Sounds like something for us. It's a little slow, but it requires just function and x0. Yeah. So then we can get that q is equal to f solve. We need function because this function just accepts q, so we have to write it that this is constraints system q 0, because we will solve it just for time 0. And then of course we need to provide it with x0. And firstly, let's check if it works. It works. Completed. And now, yeah, let's check what is the norm of constraints for sys, our new q that we get from fsolve and 0. That's pretty good 0, numerical 0. Yeah. So yeah, so we can decode it. Where is 0? It's 0, like here and here. So those are some values. 50, as we expect, from this sine of 30. Yeah. Uh, it seems that this is minus 30 degrees. Why not? And some others that makes sense. Okay, works. So now we were able to solve our system on kinematic level. And you can use even this code to solve all the stuff on kinematic level. Then you can write here a loop for t equal from 0 to 10, for example, and get q for all time instants, yeah, by just simply putting t here. Yeah, so we have done a lot of work to make it happen, and it works, which is super nice. At least, yeah, I like when it works and when it's useful. Now our goal will be to use Newton-Raphson, but of course now we are run out of time, so we will implement it next time. So we need a Jacobian, and then we'll use Newton-Raphson. We will compare how much faster is Newton-Raphson as compared to fsolve, and also we need Jacobian for velocity and acceleration. So there is many reasons why we want to go with Newton-Raphson. But I wanted to get there because it also means that you can start working on assignment. Yeah, because now you are free from assignments from this course. So the next assignment, that I think it will be double the points than previous assignment, and the very final assignment will be triple the points. Yeah, so the weight. Yeah, because now you get points for 3 assignments already. Yeah, maybe some of them resubmit them, so I will check them soon. Yeah, but you get those points, and those points has some weights, and weights from the assignment up to now are 1. I have to talk with Alexander if he wants to give you 2, for example, because I don't know if it was more challenging or not. Yeah, but this assignment will have weight 2, and the very last assignment that we'll do with dynamics will have weight 3, and then all those points will be weighted. We'll get where it is, and then then they will be transformed to grades. Make sense? Sure. By the way, I will set up very soon gradebook. Yeah. So then you will be able to follow your grades. But of course, now all of you will have most likely zero. Yeah, because it's not likely that for the assignment till now you will have enough. But after that, you could have already enough to pass, get the pass grade. But of course, I encourage you to get to be here to the end. But okay, this assignment is to implement some missing features. Of course, you cannot do everything because we still haven't done everything, but for sure, you can work on the first point, support for transactional joints. Because we have all the stuff working up to the level that we solve the kinematics, yeah? So like it's note here, so we can implement transactional joint and replace it replace this simple constraint for the slider with your transactional joint, and you must get, maybe that way, if it's done correctly, you must get exactly the same results. Because topologically, the mechanism will be the same. Just equations are slightly different, but everything is the same, okay? You shouldn't do now kinematic analysis on acceleration level because we still have no material to go for velocity level. So you'll be able to do this after next classes, yeah, after our next lectures. You can already think about analysis of some not analyzed mechanism. It means that in this point that analyze something that it's not slider crank and something that it's not simple pendulum, and to make it make any kind of sense, it must include transactional joints that you are going to develop, yeah? So figure out some mechanism, planar mechanism that you can describe with revolute joints, simple joints, and transactional joints. Add some kinematic excitation there. Then you should be able to define the system like here by adding appropriate bodies and the joints. And the rest of the code to solve it, like here, is the same. Yeah. Because what should be different is this definition part. And the rest is the same, yeah. Around 2 weeks and write a brief report. Any questions? So still you can do a majority of this task, yeah, like especially this find a mechanism, like this quick return mechanism or many others. I'm sure there are books, there are internet materials, there's plenty of the sources where to find this kind of mechanism. People through ages, create a lot of them. And only this part cannot be done well, yeah, but you can work on this, and I think that it could take you a while as well. Then of course you can work on translational joints on the position level, because then next you should go to also to get Jacobian out of it. And gamma vector. But we will talk about this about acceleration level analysis later. Questions? Thoughts? If you have questions like many others, just write me an email. Or you can just ask and we can just meet and discuss. Yeah, if you will have more questions. And yeah, well, like from my side, if you have no questions at the moment, that's all. Okay, so thank you. See you in a week. And yeah, let's be in touch.